So, we start this lecture with the definition of vector spaces. So, let us define vector space. So, a vector space V over the field R. So, here V is the set of vectors and R is a field of scalars. In general, we can define vector space over any arbitrary field, but in machine learning we usually have vectors, those are defined over the field of real numbers. So, in this course we will focus on the vectors or vector spaces, those are defined over the field of real number. So, vector space VR over a field R is a set of a set on which two operations let us say vector addition denoted by plus. So, this plus is defining the vector addition and scalar multiplication let us denote it by dot are defined. So, these two operations are well defined on V and R such that the first property, the set of vector V together with the operation addition of vectors forms an abelian group. So, here forming abelian group means the set of vectors with respect to this vector addition operation satisfies certain properties. One is closure property, another one is commutative property, associative property, existence of additive identity and existence of additive inverse. So, we will make it more clear by taking some example. The second property is the operation scalar multiplication is defined between scalars, that is the elements of the field R, and vectors such that for all A belongs to R and V belongs to V, we have A dot V belongs to V. The third property is for all A belongs to R and any two vectors V W belongs to V, we have A multiplied with the addition of vectors V and W equals to A dot V plus A dot W. The fourth property is for any two arbitrary scalars belongs to the field R and V belongs to V, we have A plus B multiplied with V equals to A dot V plus B dot V. The fifth property is for all A B belongs to R and vector V belongs to the set V, which is a set of vectors. The product of A B scalar multiplication with V equals to A B dot V. So, in left hand side we are multiplying A and B first and then we are multiplying this scalar to the vector V, while on right hand side we are multiplying B first with V and then the vector B dot V we are multiplying with the scalar A. And the last property is that is called unitary law. So, what is this unitary law? So, there exists one belongs to R such that if you multiply this identity scalar with any of the vector V belongs to V, then this is equals to V for all V belongs to capital V. So, if a set of vectors V satisfy all these 6 properties with respect to these two operations, then we say that V together with these two operations is a vector space. So, now we will take some of the examples of vector spaces. So, my first example is coming from the vector space R2. So, here R2 is a plane, you can take it as xy plane and each of the point of this plane is given by a vector, that is pair of point x and y, where first component is the x coordinate of that point and the second component is y coordinate of that point. So, this R2 forms a vector space over the field of real numbers. So, to check this we have to see whether it is satisfying all these 6 properties. So, let us see. So, property 1 is, first I am taking 2 vectors or 2 points in R2 plane, that is A B and C D. So, these are 2 vectors V and W, let us say, from the vector set capital V, which is R2, then A B plus C D. So, how we add the vector? We add the first component with the first component of the second vector and the second component of the first vector with the second component of the second vector. So, A B plus C D becomes A plus C comma P plus D. Again A plus C is a point in R2, which is x coordinate of a point in R2. Similarly, P plus D is the y coordinate of a point in R2. So, if you add these 2 points, again we are getting a point in R2. So, we can say that closure property holds in R2. Similarly, if I take again the AB plus CD, it is equals to A plus C comma P plus D. I can write A plus C as C plus A comma D plus B, and which is nothing just CD plus AB. Hence, the order of the vectors in addition does not matter, and we are saying that commutative property holds in R2. If you take 3 vectors, let us say AB, CD and EF, then first I am adding here CD plus EF, and then whatever result I am getting, I am adding AB into it. So, it will become AB plus C plus E comma D plus F. Now, I can write it A plus C plus E comma B plus D plus F. Since these are scalars, these are real numbers, so they satisfy the associative property. So, A plus C plus E, I can write A plus C plus E. Similarly, B plus D plus F, I can write B plus D plus F. So, hence it becomes AP plus CD plus EF. Hence, associative property holds in R2. Further, if you take the origin of R2 plane, that is 0 0. So, if you add this in any vector AB, the result will come out to be AB only. So, hence 0 0 is an element of R2 and it is identity element. So, existence of identity holds here. Next, if you take AB, then certainly there will be minus A minus B also will be there R2, and if you add these 2 points, then result will come out to be 0 0, which is nothing just additive identity of R2. Hence, the existence of additive inverse hold in R2. So, these points satisfied, and they implies that R2 plus forms an abelian group. So, this is the first property which we have defined in the definition of vector space. Now, come to rest of the properties. So, my second property was there that if you are having a scalar and a vector, then the scalar multiplication between them also an element of the set R2. So, I am taking here K belongs to R, which is a scalar, AB is a vector from R2, then K multiply with AB will become K comma KB. So, again K comma KB is an element in R2, and hence the second property holds. So, now come to third property. I am taking a scalar K here and 2 vectors given by AB and CD. Then the multiplication of K with the addition of these 2 vectors AB and CD can be written in this form, K times A plus C comma B plus D. I can take K inside. So, K A plus C comma K B plus D, which is K plus K C comma K P plus K D. This I can write K comma K B plus K C comma K D, and which is nothing such K times A B plus K times C D. So, hence third property hold in R2 with respect to the operations vector addition and scalar multiplication. Now, come to the fourth property. I am taking 2 scalars K and M. Now, come to fourth property. I am taking 2 scalars K and M from the field R and a vector AB from the set of vectors R2. Then K plus M times AB can be seen as K times AB plus M times AB. So, hence fourth property holds in R2. Now, come to fifth property. So, here again I am taking 2 scalars from the field of real numbers K and M and a vector element AB from R2. Then K times M times A comma B can be written as K ma comma mb, which is nothing, just I can take k inside again the bracket, k times ma comma k times mb, and this finally comes out to be km times a comma b, which is the fifth property. Further, you know that 1 belongs to the field R, means 1 is a real number, and if you multiply 1 with any vector a b, it will be 1 comma a comma 1 comma b, and it is nothing, just if you multiply 1 to any real number, the real number will remain same. So, it is equals to a comma b. Here unitary property holds. So, here all m1 to m6 are satisfied, and therefore, we can say R2 on the field of real number with respect to the operation set addition of vectors and scalar multiplication is a vector space. So, this is an example of R2. Similarly, we can show that R3 is also a vector space, and any set of vectors like Rn, where each vector is having the n components x1, x2 up to xn, also forms a vector space. So, this we have talked about R2, R3 and Rn, these kind of vector spaces, those are very common in machine learning, but the same time the set of matrices of order m by n. So, where m and n are real integers, so positive integers in fact. So, any matrix of order m by n forms a vector space over the usual addition of matrices and the scalar multiplication. So, there are many other examples of vector spaces. As I told you, Rn forms a vector space over the field R. If you take the set of vectors of all polynomials in variable x and having real coefficient, then this set also forms a vector space over the field R. Similarly, if you take a set of all polynomials of degree at most n, so degree either n or less than n in variable x and having real coefficient, then this set also forms a vector space over the field of real numbers with respect to the operations usual polynomial addition and scalar multiplication. If you take V as the set of all convergent sequences, then this set also forms a vector space over the field of real numbers where the operations are usual sequence addition and scalar multiplication. So far we have seen many examples of vector spaces. Let us see some of the set those do not form vector spaces. So, my first example is set of all polynomials of degree n does not form a vector space over R. Why? Because vector addition is not closed. So, if you want to see this, so let us set two elements from V. So, here V is set of all polynomials of degree n. So, let us take n equals to 3. So, I am taking V as the set of all polynomials of degree 3. So, let us take two elements from this set or two vectors from this set. So, let us say V1. So, V1 I am taking, let us say 2 x cube plus 5 x square plus x plus 7, and I am taking another vector minus 2 x cube plus 3 x square plus 4 x plus 1. So, V1 V2 are two polynomials of degree 3. So, it is an element of V, it is an element of V. Now, if I take V1 plus V2, So, what will be V 1 plus V 2? So, it will become 8 x square because x cube term will be cancelled plus 5 x plus 8 and it is a polynomial of degree 2. So, hence it is not an element of V. So, hence this set do not form a vector space. So, closure property. Similarly, if you take R to R, we have seen in earlier example that if you take the usual addition of vectors in R 2 and the scale usual multiplication of real numbers, then it forms a vector space. But if you define your vector addition and scalar multiplication in this way, like if you are having vector x 1 y 1 from R 2 and another vector x 2 y 2 from R 2, then their sum is x 1 plus x 2 comma y 1 plus 2 y 2. In usual case it will be y 1 plus y 2, but we are defining this operation in this way. One can define, but if you are defining in this way, then what we will see that, so x 1 plus x 1 comma y 1 plus x 2 comma y 2. So, these are two vectors from R 2 and we are defining their vector addition as x 1 plus x 2 comma y 1 plus 2 y 2. Okay. Now, if I take the reverse order x 2 y 2 plus x 1 y 1, then it will become x 1 plus x 2, first component will be the same as in the previous case. However, in the second case it will become y 2 plus 2 y 1. So, now this second y coordinate of these vectors, so it is y 1 plus 2 y 2, it is y 2 plus 2 y 1, sorry, y 2 plus 2 y 1, hence both are not equal. So, what we can say, x 1 y 1 plus x 2 y 2 not equals to x 2 y 2 plus x 1 y 1 in general for all vectors in R 2. So, what I can say that commutative property does not hold. So, hence if you are defining your vector addition in this way by this operation, then it R 2 on the field of real numbers does not form a vector space. So, what we can say from here, the only set is not important in the definition of vector space, but the operations also, how you are defining your operations. For a particular set, one set of operations will satisfy all the 6 properties of vector space, but if you change the operation, it may happen that the particular set does not form a vector space. So, you have to be careful in this case. Now, we are coming to geometric interpretation of R 2 and R 3. So, what we can have for n equals to 1, 2 or 3, the space Rn has a very useful geometric interpretation. For any greater than 3 we cannot see in general, but for n equals to 1, 2 or 3 we can have this beautiful geometric interpretation. How? Let me explain it. So, for n equals to 1 we are having the set V equals to R and the vectors will be like V equals to X. So, how you will see geometrically this vector? So, on the real line you will be having the origin, let us say 0 here, and then 1, 2, 3 and so on. Similarly, here -1, -2, -3 and so on. So, we are having this real line. Now, if we are having a vector, let us say V equals to X equals to 5. So, what will be this X equals to 5? So, let us say 5 is here. So, the tail of this vector will be here at 0 and then we are having the head here at 5. So, this is the vector V equals to 5. Similarly, if I am having something like V equals to -2. So, V equals to -2 will be again tail will be here and I will be having this. So, by the green color I am showing you the vector V equals to -2 and by the blue color I am showing you the vector V equals to 5. Similarly, for n equals to 2. So, now it is set of vector is R2 and the vector will be something like V equals to xy. So, in coordinate plane xy, this vector will be having tail at the origin and suppose this is the point xy. So, this straight line joining the origin and the point xy will show the vector V. For n equals to 3, we are having the 3-dimensional coordinate plane. So, let us say x, y and z and I am having a point, let us say x, y, z here. So, again it will be a line in 3D having tail at the origin and head at the point x, y, z. So, this is my vector V equals to x, y, z. So, if you are having two vectors, let us say V1 equals to x1, y1, z1 and V2 equals to x2, y2, z2, both are in R3, then V1 plus V2 will be x1 plus x2, y1 plus y2 and z1 plus z2, which is again a vector in R3 because R3 forms a vector space. And how to see these? So, let us say this is my vector v1, this is my vector v2, then the sum of v1 plus v2 is given by the diagonal of this parallelogram. So, this is my v1 plus v2. One more important remark here, if v1, v2 and v3 are linearly independent, so what is the meaning of geometrically of this sentence? So, it means v1 and v2 are not collinear and the vector v3 does not lie in the plane of v1 and v2. So, these are some geometrical interpretation of vectors in R2, R3. Similarly, we are having Euclidean space Rn, where we are having the vectors coming from n tuples, like a vector x is x1, x2 up to xn. So, Euclidean space is used to mathematically represent physical space with notions such as distance, length, angles, although it becomes hard to visualize for any when n is greater than 3. That is why I have given geometrical interpretation up to R3 only. However, these concepts generalize mathematically in obvious way, and in machine learning also we will have vectors, those are having huge dimensions. So, like dimension, let us say n equals to 100 or let us say n equals to 1000. So, it will depend on your data set and the feature those you have been extracted from your data. So, how many attributes you are taking for a particular feature vector. So, this is all about vector spaces. In the next lecture, we will learn about subspaces, that like we are having the set of vectors here V. So, if you are having subset of V, when they will be itself a vector spaces. Then we will see some of the properties of subspaces, those are quite useful in machine learning, and then we will see some of the numerical examples. So, these are the references. So, I hope you have enjoyed the lecture. Thank you very much.